Okay, this must be lecture 13, and this will be the first half of chapter 8 on estimation, also known as confidence intervals. And for those of you who haven't seen me, I am your instructor, and several of you have been in the office hours, and I've seen many of you, and although there's no obligation for you to have your camera on when you join the office hours, but feel free to do so, and we'll get to the lecture right now. And so here we are, estimation of the mean, also known as confidence intervals. We'll also get to the proportion later on in the chapter. The first one's a brief introductory experience, as many of them are in the beginning of this book. So the opening example would be, and I've taught the nursing statistics for many years, this isn't it of course, but if you did plan to become a registered nurse, do you know how much registered nurses earn per year? And back 6 years ago, they earned around $70,000, and they vary greatly from state to state. California seemed to be the highest. This was 6 years ago, so that's not such a bad profession to be in, I imagine, especially nowadays. Anyway, the average was only about $62,700 in Florida, so Florida was quite a bit less than California. So we have the assignment of values to a population parameter such as the mean based on a value of corresponding sample statistics, and it's called estimation. We get something from a sample, we try to apply it to the population. And the value assigned or values assigned to the parameter such as the mean based on the value of a sample statistic, like sample mean, is called an estimate. Sometimes they're good, sometimes they're not as good. The sample statistic used to estimate a population parameter is called an estimator. And so the procedure, which was covered in chapters we did not get to in the beginning of the class, we had stuff that wasn't necessary for us. This is about all we need for our class. The idea would be select a sample, a representative sample. Convenience samples are almost never good enough, but there are many other types of samples, random samples. Collect the required information from the members of the sample, calculate the value of the sample statistics, such as X bar, and assign values to the corresponding population parameter, such as mu. The value of a sample statistic that is used to estimate a parameter is called a point estimate, and these are amongst the easiest problems in the entire class because they typically just give it to you and you just copy it down if we ever ask you for it. I rarely bother to ask because it's so obvious. But in interval estimation, which is more important to us, confidence intervals, we'll get to that, an interval is constructed around the point estimate. Point estimate is typically in the center. As far as this class, it'll always be in the center. And it's stated that this interval contains the corresponding parameter with a certain confidence level, such as 95%. There's also 90 and 99 and various others. The number we assign or we add to and subtract from the point estimate is called the margin of error or the maximum error of estimate. Margin of error is a very popular term. I've seen it abbreviated as MOE sometimes, but margin of error is what we'll use. And so here would be a kind of a picture. If we had our X bar at 2970, and maybe somehow later on we found out that the mu is different, it typically is different, our confidence interval might start at 2630 and end at 3310, and that number is halfway between our two ends of the confidence interval. So each interval is constructed with regard to a given confidence level. It's called a confidence interval. This is such a popular term, we will always abbreviate it CI, at least I will. And the confidence level is given as point estimate, that is 2 words, plus or minus the margin of error, also known as of error. And yeah, the plus and minus is key here. So you've got some sort of point estimate such as X bar, plus or minus, margin of error, call it E if you like. Some books call it little m. And the confidence level associated with the confidence interval states how much confidence we have that this interval contains the true population parameter, such as 95%. And easily you can find that alpha is 0.05 here, but we'll talk more about that later. And that's it for 8.1. That was a short one. 8.2, a little bit longer. estimation of the population mean, which is mu, and sigma is known. So sigma, little sigma, of course, is known. This lets us use z, something we are more familiar with. It is also considered to be less realistic, and many books give it very short coverage. However, I find it's good for a couple of reasons. It gets you familiar with the process without having to also learn a new distribution at the same time, something that most students find quite distracting. And I worked for the Forest Service back when we had such stable data that Z was often used because we didn't have to worry about the level of uncertainty that is considered to be, more important nowadays. This is only like 25 years ago. But anyway, 3 possible cases, and the book gets repetitious about this, so I'm only going to cover this like once. If the following 3 conditions are fulfilled, and we know the standard deviation, that's kind of going into 8.2, so we know that's the case for 8.2 to even be in effect. Later on, we'll change it up. However, we might have the 2 more important situations where maybe our sample size is small. Not a good thing, less than 30. But what saves us is we have a normally distributed, or at least approximately normally distributed, set of data from well-known types of data. And so once we have normal, we're saved. I think we've seen this before. Oh, there's another case. Yeah, sigma is still known. And here the sample size is large. And then we don't even care about normal. Normal? That's nice. Don't need it, though. Normal doesn't matter. It's provided n is greater than 30, we're good. So we've seen this kind of idea used before. Your book really loves it. They present it in seems like 4 or 5 different sections. I think once you've heard it, you don't need it again, do you? And there is a third case the book does mention that I chose to ignore because we're not going to run into it. If we did have n less than 30 and not normal or not assumed to be normal, then call the statistician because this is not going to be used in 262. So that's your third case. Enough said about that. We're not going to be seeing any questions like that, except possibly in web work. Web work goes in so many different directions, I can't keep up with them. And if you do see a small sample and there's no mention of normality, you simply can't do it. It's more advanced statistics, which we don't have time for. Okay, so we have the idea of the confidence interval, and they forgot to put a few of the symbols in the transfer. So here's how we would get this to go. X bar is the representation of the population parameter mu. That's all we have. We have X bar from our sample. There's a value of Z that we'll get to in a minute depending on our confidence level. And sigma sub X bar, which is here, we've seen this before, it's simply sigma divided by square root of n. In fact, the way I learned it was just to bundle it together, but those using calculators appreciated being separated. But this is just the way I use it. And if you're doing your calculations by hand, why not just do it all together? But as you have a choice. 2 steps or 1, you take your pick, as long as you show some steps. And I really appreciate those on the midterm, which I'm around half done grading as of this recording. I appreciate you showing your work. Yes, you not only get more points, you make me happier. Those who just pretend as if one number will do, well, the frown starts to come out, and so does the red ink. What can I say? That's the way I've always graded, and that's the way everybody I know has always graded. So margin of error would be the idea of getting Z times sigma sub X bar, or simply Z of sigma divided by the square root of n. And this is a sigma. Make sure you can see that. And that is the margin of error. That's before the X bar plus and minus. That was off to the side. The margin of error is what follows it, this term here, or the briefer term if you prefer. That's the quantity that's subtracted from and added to the value of X bar to obtain the confidence interval. You start with the point estimate X bar, and then you fan it out by putting in that margin of error. That gives you an interval, which you're confident in, a certain level of confidence. Here's probably the most important example that we see, although there's a variety of others. For a 95% confidence level, you're going to have an area of confidence, which is in the centered 95%. It's always in the center. So because there's 5% where you're not confident, the area of non-confidence, called the critical region, you divide that by 2, and you get really 2.5% in each tail. Left tail and right tail, there they are, 0.025. Decimals are generally preferred, but one of those statistical traditions, they always say a percent confidence interval. I've really never seen 0.95 confidence before. I suppose it could be done, but it's just not standard. If you happen to put it on a test that way, I guess I understand what you mean, but it just isn't what's done, so I have to tell you to try to conform so everybody else knows what you're talking about. So anyway, the point is, you've got the area of confidence right in the center, and yet the area outside that you're not confident of. Either it's too small or too large. So the area in the tails, this is a pretty important one. We have the idea of the 95% giving us very popular values of z, plus and minus 1.96, corresponding with the 95%. This time I'll use percentages, and the alpha over 2. Well, what was alpha? Well, see, alpha would be 1 minus 95%, 0.95, which is 0.05. That's kind of like the decimal experience for non-confidence area, the critical region. They like to cut alpha in 2 because almost all of these are two-tailed situations, and so we do have 0.025. 2.5%, I suppose you could say. They have different styles for different aspects of it. The stuff in the center just about always gets a percentage, and the stuff in the tails typically doesn't. Well, I can't tell you why they did that, but that's just what they generally do. But as long as I see the correct numbers, that's the main thing. And these Z numbers that we see here are very popular. You're going to be seeing them a few more times. In fact, here are 3 of the more popular ones. I'll just put check marks on the ones that I put on my own PowerPoint, which I'm not sure if I will show it to you because it's kind of going to be redundant after the slides presented by the book are kind of through. Yeah, so anyway, with 90% confidence, we have a kind of a narrow region. It's more precise. That part's pretty good. And our Z value is plus and minus only 1.65. So precision is good. But the thing is, with 90% confidence, you're wrong 10% of the time. 10% incorrect. And in many cases, that is just not acceptable. The golden standard is 95%. Seems to be a good balance between having some precision, which we already saw, but we're going to be wrong still 5% of the time. That's generally considered acceptable. What about that third option? Well, you're not going to be wrong very often. You're going to be wrong only 1% of the time. A lot of people like that a lot. Trouble is, this plus and minus Z value here is not very precise. It gives you wide confidence areas, such as with a proportion being between 10% and 90%, or 0.10 and 0.90. That is so vague that it's worthless. And there are times where you get confidence intervals that wide that are just worthless. However, you're not going to have to worry about that in this class. You'll always get these confidence levels defined for you in advance. And the book, of course, does extend it into further modes. They even have a 97% here and there. But the ones that I put check marks on are the ones that you will see the most often. And if you were looking in the table to double check your work, yeah, the 90% has 5% in each tail, 0.05 in the left, and then cumulatively speaking, 0.95, which is 0.05 in the right side, by the way. So if you want to double check these in your table, you could do them. And this seems to be the golden standard here, but we have others that have only 0.5% in each tail. Notice that's 0.5%, and this is 1 minus 0.5% on the right side, so that really extends it quite a bit. And your book uses 2 decimals. Now, I do have another set of slides that uses 3 in some cases, and you may use 3 if you wish. Certainly if you're using a calculator, you can use 3. But for the rest of you, I prefer you use 2. It just saves me time in grading. Here's an example. A publishing company just published a new textbook. Before the company decides the price at which to sell this textbook, it wants to know the average price of all such textbooks in the market. So it takes a sample of 25 comparable textbooks, got the information, found the mean X bar of 145. But it is known, keyword known, that the standard deviation for the prices is 35. So that says it is not S, right? That says that's sigma. This is not from a sample. This is from a sample, this of course being N, and this is the sample mean. So let me just point and say that is X bar, and that's the key difference. But when you have sigma, you are allowed to use the Z distribution, kind of the main distribution. We'll break away from that in the next lecture. We'll show you the difference, although that's the only difference. We're going to get the setup going here for the next couple of chapters almost. Anyway, why does the point estimate of the mean price of all such textbooks? Some of the easiest problems in the entire book are point estimate problems. They told us it was 145 bucks. Guess what? That's the answer. And you don't even have to show your work. How about that? Even I make exceptions. Not very many of them, but this is one of them. But now they'd like to get a 90% confidence interval for the mean price of all such college textbooks. Well, we know for sure that this is going to be 145 plus or minus a margin of error. And you may use the dollar sign if you wish. That's going to give us Z times sigma over square root of N. Sigma sub X bar if you prefer to use a calculator to input it that way. And yes, I'll put the 145 here. So we need to look up the Z. It's probably best to memorize them, but that was the whole idea of the page of notes, is to be able to have these at your fingertips. And back here we see that 90% gives us plus and minus 1.65. So let's go to the next slide. And now we have N is 25, X bar is 145, and sigma by itself is 35. The point estimate of mu is X bar equaling 145. What could be easier? Well, sigma sub X bar, if you choose to separate that out, is sigma over square root of N, which is 35 over the remarkably simple square root of 25. 35 over 5 is 7. Don't use your calculator for that one. Okay, so now we've got our sigma and we have our Z. Remember that was plus and minus 1.65. That's the magic value of Z for a 90% level or 90% confidence interval, abbreviated CI. Let's see how they apply that. So alpha over 2 is equal to 1 minus 0.90 over 2, which is 0.05, which if you look up in the table, you would find, especially if you looked on the left side of the table, you'd find your minus version. On the high side of the table at 0.95, you get the plus version. So really, we kind of bundle them together. And notice the formula already has the plus and minus built in, so that's not so much of an issue. And so we do have 145 plus and minus 11.55. How did they get that? Well, it's very distracting to me to have all these little symbols wilt away on me. It wasn't there the last time I looked at it. They were there the last time I looked at it. So we have sigma X bar plus or minus Z sigma, which is equal to the 145, the point estimate, plus or minus the Z value, 1.65. That's multiplied by 7, which was the result that we just got from before. We just got that from the prior slide. So we're looking at plus or minus 11.55. And so what they're trying to do here is to go from 145 minus 1155 to 145 plus 1155. So you've got a negative version on one side and a positive version on the other. So it's very simple just to add them. And here is your confidence interval. We're 90% certain that the true mean of the textbooks would land between about $133.50 up to $156.50. However, we're 10% sure that it does not land in that interval. 5% on the left, that is lower than 133, and 5% on the right, higher than 156.55, and that's what our statement would be. So this just summarizes what I just said, 90% confident that the mean price of all textbooks, that genre, is between those two numbers. Okay, confidence intervals. The thing is, you do get different samples. Different samples almost always yield different results. Perhaps we got one over here. Maybe this was the first one. Maybe this was the second one. And maybe this was the third one. And they're not the same. In fact, that X bar 3 is pretty far away from X bar 1. That'll happen from time to time, such as when you have 20 pollsters. Being an election year, people will be trying to collect pollster data, although in the virus days, I'm not sure how they're going to do that exactly. But anyway, assuming that there's still pollsters around and all that, you'd figure that they get different results. And it could be that 1 or 2 out of the 20 might even get it wrong. With 95% accuracy, only 19 out of 20 are expected to basically hit the bullseye. And elections are one of those things like weather, where the answer does come along. The final answer does reveal itself. The weathermen only have to wait a day or two, depending how long their forecast is, maybe 7-10 days at the most. And the election results, they just check and see what the percentage of voters were that did whatever they did or didn't think they would do. And so with 95%, 19 out of 20, that's a very typical scenario. 95% is the most common one. 19 out of 20 would fit that bill. So you would expect that one of the pollsters would have an incorrect confidence interval. Okay, so that just gives you a kind of a slice of what we're up against with just 3 different samples. And we'll notice that the end of this interval is not quite overlapping with the beginning of that interval. So there's a bit of a disconnect, whereas X bar sub 2 is right in the middle and maybe considered more accurate depending on how the other data comes in. So here's another example. According to a study, an individual checking account at major U.S. banks cost them more than $380. Forget the more than, just call it $380 per year. They're just being distracting. So we have a large random sample. That's a large one. We don't have to worry about normality here. I believe the last one did mention normality. But here we do have 600. Don't have to worry about it. If they happen to say it, it's just a bonus. And it produces a mean annual cost of $500 to major U.S. banks. Now, assuming the standard deviation of annual cost to major U.S. banks is $40, and this is the standard deviation. It did say assume, so they're making it simpler for you by assuming that this is sigma, not S. Make a 99% confidence interval estimate for the current mean annual cost to major U.S. banks for such a checking account. And by the way, this 380 doesn't seem to really matter, so I'll just cross that out. Let's see how the steps go. So confidence level is 99%. Sample size is large. It is greater than 30. We don't have to worry about normality as we mentioned before. So we will use the normal distribution, and Z will equal plus and minus 2.58, the largest one that we typically see. So once again, sigma sub x bar is sigma over square root of n, excuse me, which is 40, the given sigma, divided by the n, which is square rooted and divided into it, to give us more of a standard error of the mean of 1.63 and change. And notice, lots of decimals are used. A few of you on the test were lucky to give me 1 or 2 decimals, and of course your answers weren't even close to what I was looking for. If you're not giving me at least 3 decimals, you're not even in the game. And 4 and 5 is better, actually. But once I saw at least 3 decimals, I pretty much gave you the benefit of the doubt. Of course, I rechecked it. But, if you don't want to use 8 decimals, at least use 4 or 5. That's my recommendation. And best to use as many as you can, obviously. Okay, so we have our standard deviation, or that is our confidence interval, as being x bar plus or minus z times sigma sub x bar, which is 500, which is the center mark for x bar, plus and minus the z score, 2.58, which is multiplied by what we just got, standard deviation of the mean, standard error of the mean, same thing. That works out to be pretty small margin of error. Remember, we had 600 in our sample. That tends to really narrow it down. It tends to not flatten the curve, just the direct opposite. It makes it rather steep. So that was our n. And so we have a real tight margin of error because of our large sample size. It gave us normality and a narrow spread, which is what they're after. They like precision. Mostly precision is a good thing. So when you add and subtract the numbers, there are the results. Put those equal signs in. And now we can state with 99% confidence that the current mean annual cost to major banks of all individual checking accounts is between the 495 and change and 504 and change. It's just very cookbookish. especially if you have a source like this page of notes. It just take a little time, practice this. You should find it to be quite routine. This is not meant to be a very challenging chapter. Some people make it that way. You shouldn't. You should make it pretty easy. Just look up the z-values. They're typically 3 you see over and over. Those are the only 3 that I will ever use on a test. I will tell you that. Now, I cannot guarantee you the homework, but then you just look it up and figure it out. The width of a confidence interval depends on the size of the margin of error, z times sigma sub x bar, which depends on the values of z and sigma and n, because, as we've said many, many times, we have sigma divided by square root of n. But the value of sigma is not under the control of the investigator. That's a misprint. This is a bit of random chance. It could be that you get very similar values, or values ranging from 8 to 80 and all kinds of spread in the data. You really don't have any influence on that. So that's just bad luck if your data is all spread out because of the nature of the distribution that you're surveying. But we can control the width of a confidence interval by a couple of things. I'd go to number 2 first, the sample size. If you get a very large sample size, like 10,000 or so, we already saw what 600 did. It narrowed it down to less than $5 of a margin of error. So if you get a large sample size, that's good. Large for n gives you precision, which is nearly always a good thing. Oh, the value of z also depends on the confidence level. So 90% is more precise. If you're looking for precision, 90% would be your choice. But of course, that means you're going to be wrong 10% of the time, and you have to just sort of judge it. These are typically not life and death situations when 90% is used. Life and death is exaggeration in most cases, but if that were the case, you'd want a 99%er, which does not increase the precision. It's just the opposite. And I thought I'd leave this slide in. It does show the current emphasis on nurses. How California, even 6 years ago, was doing quite well compared to most of the other big states. And so, not that any of you will be nurses, but it does look like a very exalted profession. Okay, back to the lecture. Determining the sample size for estimation of the mean. Now, this is a little bit unusual. I've taught a class that involved 6 of these calculations. We will only see a couple, maybe 3, depending how you count it. And this one will be regarding the estimation of mu. Sometimes when you're planning experiments, and I was never part of that as working as a statistician, I was walked into something that had already been started. I didn't need to pick the sample size. But sometimes they want to know how many they have to go out and survey. Did they have to get 600 or will 30 do? That kind of thing. Clearly, the less your sample size is, the easier it is for you. And if you only need to do 30 or 50 or so, go ahead and do it. Do a few more if you want. But time and resources, money, all come into play. And if this calculation says you have to get 10,000 in your sample size, that's usually pretty bad news. Maybe you have to scrub it or cut corners in another way. So we have the value of z, which is squared, and we have the value of sigma, just sigma. Notice n is not part of the calculation. We're solving for n here. So what we have here is z squared, sigma squared over e squared. And I've always found in many books they list it in a slightly easier way. This is my opinion. Why not just get that ratio, z times sigma over e, and then square it? Seems a little easier to me, a little less work. Why your book didn't think of that, I'm not quite sure. So put that in. Always round up, by the way, because it is a minimum sample size. This is a minimum sample. They didn't use that word here, but it is a minimum sample size. You can always get more. Doesn't hurt to get more, but it does hurt to get less. Here's a good example. An alumni association wants to estimate the mean debt of this year's college graduates. It's known that the population standard deviation of the debts of these year's college graduates is 11,800. Yes, S has no place in an N calculation. Also, there's no proportion here either. So some people want to use proportions for a mean calculation, really don't have a good general sense of what's going on. Mu is not the same as P. We'll get to another formula here when proportions dominate the conversation. That's next time. But here, there is no P. It's just mu. So use the mu formula. seems clear to me, but you just have to figure it out for yourself. How large a sample should be selected so the estimate with a 99% confidence level is within $800 of the population mean? Okay, now the margin of error was called E. So let's go back and see what they're talking about. The within number is always E. When you see the word within or a synonym that says the same kind of thing, use E there. So E is equal to 800. That takes care of the margin of error right away. I don't know what else is going on except for the fact that E is $800. And the mean is 11,800. We're going to need a z-score for sure. Z-score here will be equal to 2.58. Go ahead and use the positive version because it'll be squared anyway. Negative squared is positive. A few of you forgot that on the test. Yeah, when you square a negative number, it does come out positive. There are no imaginary numbers in this class. So Z, sigma, and E. Sigma is, let's see, yeah, here's the standard deviation. That is sigma. Sigma is equal to $11,800. So we have all those numbers, and now it's just a matter of putting it into your calculator and seeing what comes out. All right, so as we said earlier, E is 800. The value of Z for a 99% level or confidence interval is 2.58. And I use confidence level and confidence interval almost interchangeably. Level is just slightly removed from the interval process, but it's really about the same thing. So using the formula, they have the long-winded version. You do have Z squared sigma squared over E squared. They've squared them all individually, which I find it takes a little bit longer, but it will not make any difference if you square it on the way out. And we finally get $1,448.18. Round up. They don't make a big deal of this here, but I am, and I will on the test. It's not the same. This becomes 1,449 as the minimum required sample size. Now, 1450, no problem. 1448, that's a problem. Notice 1448 is less than the minimum. Statisticians pay attention to things like that. I'm not saying you're a statistician, maybe not yet anyway, but pay attention to the small stuff, and the big stuff should follow. So now if you get 2,000, 3,000, even better. It's like cherry on top or gravy or whatever you want to call it. But the thing is, you have to go above the minimum, and the minimum was with a decimal. On very rare occasions, the value of n comes out as a whole number. Then you don't have to round up. But I've very rarely seen cases like that. They just don't happen very often. So I really doubt you will run into that. But if you did get a whole number, then you just leave it alone. But that's pretty rare. Okay. Now, point estimate is kind of a recap on the slightly different version here. Point estimate says a single value estimate for a population parameter. Yes, we did talk about that, just a single value, which is given typically. Most unbiased point estimate of the population mean is the sample mean X bar. And although they vary from samples to samples, it is considered to be unbiased. That's a technical term that we're not going to go into too much, but there's no inherent bias in that calculation. So we estimate the population parameter, the mean mu, with the sample statistic X bar. There are others, such as estimating sigma by S, but that will not be in 262. We will not be using that. We'll be estimating P by P hat. Yes, we will be seeing that next time in 8.3. And we'll be coming up 8.3 and 8.4 the next lecture. And there are others that could be done, but we will not have time to do them in a 10-week class. Now, in this particular case, they actually wanted us to find the point estimate. This is unusual. I do not plan to give you any problems like this, but here's a random sample of 40 student athletes. They're collecting data about a college athletic conference and its student athletes. The number of hours they spend on required athletic activities in a week are recorded. Find the point estimate for the population mean. These numbers are not sorted, but it's just a mean, so we just add them up. Just sum them up and divide by 40. They actually gave us n, so we just have to find out what these are. I'll just call it sum of x, and so they go ahead and do that. A little bit boring, but it works. And we do have the sum of x over n. Turned out the grand total hours was 842, which does average to exactly, well, pretty much rounded to the nearest tenth, 21.1 hours per week. And I will we'll say this is hours per week, just to make sure that we have that in place. Now the interval estimate, which is much more important. That's what we're really talking about here. The range of values, the believable values used to estimate a population parameter, especially the mean and, of course, the population parameter called the proportion. Those would be the only ones we see. Before finding a margin of error for an interval estimate, first determine how confident you need to be that your interval estimate contains the population mean. Typically, your choices are 95, 90, and 99. Do not worry, it will be given. At least in this class. In the real world, hard to say. I would just use as a rule of thumb 95 unless you see a special reason to pick something else. Level of confidence C, this is just a notation this other resource used, and that could be considered to be 0.95, 0.90, 0.99. And just to kind of rephrase what we just did, it's the probability that the interval estimate contains the parameters such as x bar, assuming the estimation is repeated a large number of times. And I've had other books actually go through that process, collecting like 1,000 different samples. Yeah, that'd be fun. Critical values. They're the values that separate sample statistics that are probable from sample statistics that are improbable or unusual. We saw a picture of this. Is that coming up here? Yes, it is. Okay, so we have the probables in the center, shaded in blue. The unusuals are in the tails, so these would be unusual. It's called a critical region. We're very critical there, and we're not going to accept it. Unusually large, unusually small, and they're shaded in kind of a brown or beige. They do have the calculation in case you need this in case of emergency, especially in web work. They give you something that isn't in that table. But let's take a look at what would happen if C equals 90%. Also known as 0.90 for computational purposes. So 1 minus C, 1 minus alpha, and alpha is another name for this, by the way, would be 0.10. Half of that for each tail is 5%. So we have 5% in each tail. And so this book uses 3 decimals in a couple of cases. It turned out that the values were almost exactly halfway between 1.65 and 1.64. And you may use the 3 decimal version, but I do not want you to use 1.64. That will be dinged. It is not equal to 1.64. The book does seem to say it's okay. I've noticed some people are thinking outside of the book quite literally. I do use the book as the standard. So if you're using a different resource, don't expect to get full credit all the time, because sometimes it's just not quite the way it is. And so I'm sorry, we're going to use our book as the standard here. And if you want to use 3 decimals, use 1.645 plus and minus, and 2 decimals, we'll want to use 1.65, not 1.64. So expect to be dinged if you use that number that isn't quite correct. Okay, so you have a choice between 3 decimals or 2 decimals here, and those are the critical values, plus and minus 1.645 in this particular case. Okay, if the level of confidence is 90%, this means that we're 90% confident that the interval contains the population mean. A little less confident, but it's a more precise interval. This is narrower, and so they've decided to go ahead and show you how that would go. 1/2 times 1 minus C, and 1/2 times 1 minus C. And so we kind of looked at that just now. And we have our particular values, the minus 1.65, the plus 1.645. And so z-scores are plus and minus 1.645. If you're using certain formulas, such as the confidence interval, or even the solving for n formula, you don't have to worry about the plus and minus, because it's either built into the formula or it squares away the negative version and becomes positive anyway. N, of course, should never be negative. Once in a while I get somebody who tells me n is negative 100. Well, good luck with that one. Okay, sampling error, the difference between the point estimate and the actual population parameter value. That's going to happen. That's why different samples give different results almost every time. Once in a while you get a couple that are either a tie or virtually a tie, but that's unusual. Usually they're off by a little bit, and that's just natural sampling error. That's part of the game in statistics. We're different than math. Math is just rock solid no matter what. carved in stone. Statistics, not quite the same way. So for mu, the sampling error is the difference of x bar minus mu. Hopefully it's close to zero, or even zero itself. That'd be the best, hitting a bullseye. But we don't count on hitting a bullseye. We just want to be close to it. And we realize sometimes we're not going to be. That's the frustrating thing about it. Mu is generally unknown. If we knew what mu was, we would have very little reason to get x bar. Sometimes for illustrative purposes, the book might do that, but that would not happen in the real world. If we already knew mu, what would we waste our time with a sample mean? So generally unknown, pretty much always unknown. I'll just say it that way. The x bar, of course, varies from sample to sample, which is sad truth. The margin of error, sometimes the margin of error of estimate is called tolerance, and the margin of error for mu, where sigma is known, because if sigma is unknown, we're in a different section and a different distribution, but that's for later. Greatest possible distance between the point estimate and the value of the parameter it is estimating, denoted by the margin of error E. And this is kind of a rehash of what we did. I just want to get to some other examples. Z times sigma sub x bar, or Z times sigma over square root of n. This version does use this little thing of C, but keep in mind that Z is only going to equal one of those magic values, 1.65, 1.94, or 2.58. There are 3 different decimal versions on a couple of these if you want to use them. So this book makes a lot less of a big fuss about when you can use it. It's either going to be normally distributed or n is greater than 30, maybe even both. But if you don't have either one, then you're in trouble and you simply can't do it. There would not be any of those questions on the test. I'll just tell you that. Because there's not going to be a whole bunch of them you say, cannot do, and you're done with the test in 5 minutes. That's not going to happen. I've had some students thought it was the case, but it was never the case, and that was that people know in advance. Use the data and example and a 95% confidence level to find the margin of error for the mean number of hours spent on the required athletic activities for all the student athletes. We will assume that sigma is equal to 2.3. Now 95% is the ultra standard value of z being 1.96, either plus or minus 1.96. Now, because sigma is known, sigma equals 2.3, the sample is random. Oh, by the way, n is equal to 40. That is greater than 30. They forgot to mention normal, didn't matter. So we can use the formula for E. And so the z-score that corresponds to the 95% confidence level, ultra popular 1.96. Typically in semester classes, you see this time and time again. We don't have quite enough time on the clock to see this very often, but this is one worth memorizing. Pretty close to 2 from that empirical rule that I did not emphasize. No coverage at all on the empirical rule, but this is close to 2, which is also close to 95%. That's 95.4%, by the way, but we want just 95%. And so they fall between 1.96 standard deviations of the mean on either side. So I could say plus or minus on that to clarify just a little bit. And here's a picture, along with the magic numbers, plus and minus 1.96. And this one of the more important sketches in the class, because we see this so often, seems to be the go-to in many, many cases. 95% in the center, 2.5% in each of the tails, a total of 5% where you're not confident, you're critical, a critical region. And most books, they show that as kind of the dark side, like Star Wars or something like that. Here, it's actually the light side, ironically. Okay, so using the values z, or z sub c if you prefer, equal to 1.96, sigma equal to 2.3, and of course n equal to 40, which means it doesn't have to be normal, then the margin of error would equal z times sigma over n, and the c's just don't matter. That's just a notation that's used sometimes. So 1.96 times 2.3 over square root of 40 is 0.7. I would have preferred they go to 2 decimals. This presentation did not do that, strangely. But you are 95% confident that the margin of error for the population mean is about 0.7 hours. I would prefer to see a couple of decimals on this one. So the confidence interval, as we said, was that we have x bar plus and minus the margin of error, which is the same, where z is equal to zc, or just z, times sigma over square root of n. And so this is kind of redundant, I guess. The probability of the confidence interval contains the mu is C, assuming that the estimation process is repeated a large number of times, which it could be, may not be due to time restraints, budget restraints, etc. So finding the confidence interval for a population where the sigma is known, that's all we're talking about in this lecture. Sigma unknown will be dealt another day. That's actually 8.3. So verify that sigma is known. So just make sure it's written down, like sigma equals 10, or it's assumed or well known that the standard deviation is blah, 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 and then that's a sigma. It isn't coming from a sample. That's the mean came from a sample, but not the standard deviation. And that may not happen a lot, but it does happen often enough that they do have a section for it, and we don't have to learn the t-distribution at the same time as all of this. So that double whammy is usually not so easy for many students to get. But anyway, we do have the fact that it's either normal or large enough, greater than 30. So find the statistics n and x bar. So x bar is equal to x over n, the sum of the x's over n. If they haven't given it to you already, which they usually do, I don't plan to make you calculate that. We've already been there. So let's see, constructing confidence intervals from U. Continuing with this thought, find the critical value z and use table 4 that corresponds to the given level of confidence. The 3 that I listed are the only ones that I will have you use. So of course we find the margin of error, which we've already done. E is equal to z over times sigma over square root of n. C if you want. Some books use z asterisk, different notations for different books. Z is fine. Find the left and right endpoints. Form the confidence interval. So of course you have to subtract to get to the left and add to get to the right. And so we're really looking at in a inequality form where mu is in between x bar minus e and x bar plus e. Always present it in that order. If you start with a large number first and the small number second, it doesn't make any sense. It's written backwards and it just looks kind of dumb. Are you saying that 10 is less than 4? I've had a lot of people try to tell me that, and I still don't believe them. Okay, so using the data in this example, construct a 95% confidence interval for the mean number of hours spent on the athletic activities by all the athletes in the conference. And we found that x bar was equal to 21.1. That's not really going anywhere, but we did find that the margin of error was 0.7. So, very easy calculations. If you've had calculus, this should be like very simple. Subtract the 0.7, add the 0.7, that's all you have to do. Add one, subtract the other, put them in order, you're done. And yes, one way of saying it is to put the mu in between. This has the advantage of being specific, having the mu exactly where it is, and there's no doubt about what you're talking about. There's no getting off topic, difference of mu's, difference of proportions, or whatever it may be. This is very clear. But there are other possibilities. You could, if you want, you could use the interval notation. You could say 20.4 through 21.8. But if you use this algebraic notation, it must be exact, only use parentheses, must put a comma in between. Any deviation from that, points come off. And I also will add, use the same level of accuracy, such as tenths here. Don't give me tenths and millionths. I've seen people do that. Even if you're off by 1 decimal, that's not good. Put the zeros in the back, that's fine. 2.00, that's fine. But choose your level of accuracy, which I think should at least be tenths or hundredths, if not more, and keep it. Don't change it. It just mixes your message and it doesn't look very professional. So, and you could even just use 2. Sometimes informally, you could just say from 20.4 to 21.8. So these are all possibilities. Pick one of the 3 you like and use it. And there's even a number line approach. Yeah, they forgot their decimals, they forgot their inequalities, and yes, there's a number line. Amazing, huh? No, I do not need number lines. So, with 95% confidence, you say that the population mean hours spent on required athletic activities will be from around 20.4 hours to 21.8 hours. You can even get to minutes if you really, really had to. There's no need for that. But yeah, that's a pretty tight interval. And they only had 40 people. So this is already data that was centered in pretty tightly. So we had very tight spread already, and with a sample, it's even tighter. And we got normality on top of that once we got past 30. Here's another example. A college admissions director wishes to estimate the mean age of all students currently enrolled. Now this time they have a sample of only 20 students, and the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years. Is that S? No, it's not. That's sigma. So let's put in some of these key notations. That's sigma, that's N, and of course that's your X bar. Now, we did notice that they said normally distributed, so 20 is okay. Normal saved us. Without that part of the sentence, you would have had to throw it out because we could not use it here. So you just have to put a note saying can't be done, but I do not include problems like that on the test. If you find you're doing one of those on the test, think twice. Think twice. Web work, I have no guarantees for you. So we're looking for a 90% confidence interval of the population mean age. So using n equal only to 20 and x equal to 22.9, x bar that is, and we also had our standard deviation given sigma equaling 1.5, and from the 90% confidence level, you got 1.645. You may, if you prefer, use 1.65. I'll let you choose, but do not use 1.64. The margin of error at the 90% confidence level is E equals Z times sigma over square root of n, which the magic value of Z in this case are using 3 decimals. There's a slight difference. Times 1.5 over square root of 20, and that number will equal 0.6. Once again, they have a bad habit of only using 1 decimal, which I don't prefer. If nothing else is out of order, I'll consider not charging you for it. But I do prefer more accuracy, please, if you can. So the confidence interval, starting at the left endpoint, going to the right endpoint, will be, on the left, x bar minus the margin of error. And to be fair, they only had the x bar given to 1 decimal. So I suppose that's all you could really get out of this. 0.6. Subtracted from 22.9, the smallest number that we could have that's believable would be 22.3. On the right side, no shocking news here. All you have to do now is to add the margin of error. Let's go ahead and do that. And we get the right-hand endpoint of 23.5. Pretty narrow spread of data. So the mean will be between 22.3 and 23.5 with 90% confidence. So that's a pretty tight range. The 90% helped to become even more precise than, say, 99 would. And of course, we have our number line graph, which I don't see any real need for, but some people like it. But you have no responsibility on this at all. 90% confidence, you can say the mean age of all the students is in between those two numbers. So we figure that if we put a confidence interval out there, that we will hit the mu 90% of the time and miss it 10% of the time, 5% on each side of the line. So mu is a fixed number. It's either in the confidence interval or not. It's kind of like mu is the sun. We all revolve around the sun. It used to be a long time ago that they thought that the solar system revolved around the earth. That's not really true. So it's incorrect to say there's a 90% probability the actual mean is in the interval. That's kind of missing the boat a little bit, although we don't really split hairs like this. This isn't that kind of class. The correct way to say it, though, is if a large number of samples is collected and a confidence interval is created for each sample, approximately 90% of these intervals will contain mu. So that's a better, clearer way to say it. So if I misspoke earlier, I apologize. But what I meant to say was a large number of samples are collected, and then 90% of those intervals will contain the true mu, which may or may not ever reveal itself. There's some fields that you never really know for sure, and that can be quite frustrating. But if you're into election surveys or if you're into weather, certain other situations maybe involving sports, that the outcome is coming up right around the corner, then it's easy to check yourself. But many other times you just don't get to do that. They depend on the theory. So although my PowerPoint I thought I had a more dramatic example, the horizontal segments represent 90% confidence for different samples of the same size. And in the long run, 9 out of 10, which you obviously know, is 90%. we will have them contain mu. So here comes the mu. Maybe comes along a little bit later and it reveals itself. And here's one interval that missed it. That one missed. Shame on them. But all the rest contained it. Maybe just barely, like here, just barely made it, but we got them all. Mu is in there one way or another on the left side or the right side, but there's only 1 out of 10 that missed it. Now, that's not to say that we couldn't have had all 10 make it, or even maybe only 8 out of 10 make it. There are probabilities assigned for that kind of thing. But in the long run, 90 out of 100, 9 out of 10 would be correct, and the other would not be, the other 10%. So given a C confidence level, which is 90, 95, or 99, a margin of error E, the minimum sample size N needed to estimate the population mean. This is just to review what we already had, and I'm going to go ahead and just say that it's equal to Z sigma over E. I recommend that you just find them separately and square it and round up. Don't forget the small print on that. So here they're going to just say the same thing, except they forget a couple of key items here. And it's all squared. So whether you square them individually or on the outside, that's up to you. But yes, please round up to the nearest whole number. And if it happens to be a whole number misspelled, then you could leave it alone, but I think you can wait a long time for an example like that. I'm not saying you won't see one, especially on web work, but I doubt it. I don't plan to give you one. So if this is unknown, you could estimate, okay, this is something we will not be doing, but if sigma was unknown, that actually gets into more advanced statistics. I've seen it done, but that's not generally covered in a beginning statistics class. Typically, when the other distribution, the t distribution, is used, we don't usually solve for n under elementary methods because we have some information missing. But I suppose S could pinch hit for it. We will just not be doing it here. Nice idea, but simply not used in an elementary class. So the researcher in that example wanted to estimate the mean number of hours spent on required athletic activities. How many student athletes must be included in the sample? So how many, what could that be? Could it be n maybe? Yeah, it is. The minimum n. And to be 95% confident that the sample mean is within, remember within is the E number, and that's of the population mean. What else could it be? So that's the idea. The 95% leads us to a Z, and we also had a sigma given earlier, so we can go back and use that. So C is 0.095, that immediately leads us to 1.96. They are linked together, and by the way, that's, if you want the third decimal, there it is. Feel free to use it anytime you like, but most people just use 2 in this particular case. Other versions went over to that third decimal if you want. We also had sigma equaling 2.3, and the margin of error, E, was given to be 0.05. So N would equal Z sigma over E, and I'll just square it on the way out. So we have 1.96 for Z, 2.3 is used for sigma, put a big dot there, and then E 0.5, and square the whole thing, and then you're good. And that number will be 81.29, but that's not enough. We don't have portions of people, and it's not a whole number, which nearly never is, almost never is. We round it up to 82. That's the researcher needing at least 82. So a better way to say it would be that n is greater than or equal to 82. It's strictly greater than 81.29, but we don't have portions of people. There are a lot of discrete numbers out there that don't need decimals. So we get rid of the decimal and round up almost every single case. So the researcher has 40 student athletes. The sample needs 42 more members. 82 is the minimum number of student athletes to include in this sample. Minimum number. So that'd be the end of this particular slideshow. We'll go into 8.3 and 8.4 next, involving what happens when sigma is unknown and we have to do something else. I guess that's not going to write very well. So